Alright, so this is Lab 3, Magnetic Field of a Bar Magnet. So a little introduction and understanding about this lab. The premise of this lab is to observe the relationship between the magnetic field of a magnet and the distance away from that magnet. Um, we know that the magnet is distance dependent, so the strength of the magnet, the magnitude of the magnet is going to be distance dependent. So we're trying to see exactly how that works. So we're given a couple of equations that we can plot in order to determine the slope and y-intercept, which we will later use to figure out the magnetic moment. And we can also create a computational model on Glowscript to compare the experimental data and the computer modeling. Alright, so here's a quick rundown of our data. Basically, we just had to, with a magnometer, we used an app. We had to just measure the distance and the magnitude in Teslas of the magnetic field. And so we did this at several locations that were required to us from on the actual lab experiment. So you can just pause and read through these values. So although the data is important, it's more important how we plot it. And so if you remember on the first slide, we had this ln of x equation, or ln of r versus ln of the magnitude. So basically we can plot that equation and we get this main y equation, from which we can derive the n equals -3 and the intercept, which is ln of k. Now these will be used to calculate the magnetic moment on the next slide. So here we go back to the formula of the magnitude of the magnetic field of the bar will be equal to kr to the n. We know that the magnitude on axis is that formula up there, right? So we can simply substitute in the values, set these equal to each other, and solve for the magnetic moment. So when we put in the r to the cubed, it would, and they're equal to each other, the r cubes would cancel out, and you'd simply be left with the e to the ln of k times that mu over 4 pi times 2u, and from there you can just calculate that u is about 2.86 times 10 to the -3rd, which is the magnetic moment. So then we looked at the at the off-axis field, and so we recorded the distance perpendicular, where the measured magnitude of the magnetic field was about 100 microteslas, and we moved vertically the same distance and recording the b-net coordinates. We corrected the y value by taking into account the magnitude on the y direction due to the earth, and we gotta subtract that. We got that the average distance perpendicular was 1.92 meters. That's where the average, b-net was 100 microts, and then the average b-net ended up coming out to about 4.8 to the -8 teslas. So here's a little Glowscript code that we wrote to calculate the magnetic field, however, with a computer model, and we can compare this to the experimental results. So basically, as you can see, I have arrows labeling what parts of the code do what. You can just read the code if you want on your own, but basically we calculate the magnetic moment value, then we calculate the magnetic field using that moment, and then we set some observation locations, which are uniform distance on either way, so kind of like a X or a cross. Alright, cool. Now we can calculate the magnetic field at a 45-degree angle, and to use this, we use the experimental value of 0.192 meters to determine the distance hypotenuse, which we found from the experiment. So this is the code for that, and we'll see the results on the next slide. Alright, so here are the results of the whole experiment as a whole. Now you can clearly see that the average magnetic field measured from the experiment was much greater than the magnetic field calculated from the Glowscript code. This could be due to other magnetic fields affecting the actual experiment, fluctuations in the magnometer, and just human error in general. Right there's a picture of the Glowscript code, and basically just shows the direction of the magnetic field and what it looks like at a 45-degree angle. So if you look at the magnet, the north positive side of the magnet would be on the right side, and the left south pole would be on the left side of the magnet. All right, cool. So a couple of quick questions. So what if we hadn't oriented the experiment to compensate for the magnetic north? Instead, laid out the meter stick at some angle. How would your results have changed? Well, technically, if it wasn't fully straight, there'd be an x and a y component, so we'd have to account for the difference in directions of both the magnetic field of the dipole bar magnet and the direction of the magnetic field of the Earth. And then what if you were to stick two magnets together, so just make a bigger magnet? Well, they would simply just behave like a larger magnet, so the directions would remain constant, right? That's like the r hat direction, but the magnitudes of the magnetic field would increase. That's the lab. Thank you for listening.